Hello, Mr. Muscarella. This is Jimmy Gaines, Block 3, with a Physcast on kinematics in 2 dimensions. And we're going to be going over the unit objectives and the conceptual ideas of kinematics in 2 dimensions. And first, we're going to talk about the differences between a vector and a scalar. So, make a small chart here. So vectors and scalars both share the same thing, and that is magnitude. They both measure this. They're both units of measurement. However, the difference between a vector and a scalar is that a vector also takes into account the direction. And to just show you an example of this, when you're traveling in a car along the highway, you'll look at your speedometer and it might say 65 miles per hour. And that is a scalar. It is measuring your speed, and if you were traveling in the opposite direction, it would also say 65 miles an hour. Whereas if it was a vector, say we were measuring velocity, if you were traveling in this direction, which would be the positive direction on a one-dimensional number line or axis, it would be 65 miles per hour. However, if you were traveling the opposite direction, in the negative direction, it would be negative 65 miles per hour. And an example of a scalar other than speed would be, say, distance or weight. So a marathon runner is running along his 26-mile race, and not taking into account which direction he's traveling on the two-dimensional plane, the race will say that it's 26.1 miles. Whereas if on the two-dimensional plane he was traveling in the negative direction, he would have traveled negative 26 miles. And how we're going to break up vectors into the y and the x vector is if I draw just the vector, which is represented by a line with an arrow at the end, of 10 meters per second. I can represent this in a right triangle. And we have lots of rules with right triangles to find our x and our y. And we can either do this through having either the x or the y and searching for an angle or the value that we don't have, or we can have the angle, say it's 60 degrees. We can use that to find x or y. And how we do that is through sine, cosine, and tangent. And how you're going to remember these are so, ka, to. And in the right triangle, we have our three sides. We have, well, in proportion to the angle. So here's our angle. We have our adjacent, our opposite, and the hypotenuse. So when you're solving for sine, say for this angle, we're solving for h. And we know the angle is 60 degrees. We take sine, so we put it sine, parenthesis, 60 equals opposite over hypotenuse. That's why the O is before the H. So if this is 15 meters, we have 15 over H, which is what we're solving for. So through algebra, we can come out to have 15 over sine 60 equals h. And that can be put into a calculator and you can find the length of your hypotenuse. And since we're finding the y or the x of a vector, which could be velocity, distance, anything that's in the context of the problem. When we're solving for these other values, they'll go directly into your chart. So you have your chart. This is just a one-dimensional chart. So we're going to make it two-dimensional. However, the details that you're given and the vectors you will see in a problem won't be on the y or the x-axis. So say you're given in a problem that an object is launched at an angle of 30 degrees at a velocity of 26 meters per second. Now this is your v naught, so your starting velocity. On the x-axis of your right triangle, you'll have v naught x and v naught y on the y. So you can use what I just showed you, whether it's tangent, cosine, or sine, to find your v naught x or your v naught y and plug that directly into your table. And that example where I was launching a projectile at an angle and a certain velocity, that would be described as projectile motion. So just to start on projectile motion, there's a building and a man hitting a golf ball off of the top of it. He's going to hit it horizontally, so not at an angle. And without the effects of gravity or air resistance, the golf ball will just travel in a directly horizontal line forever. However, because of the forces of gravity, which is negative 9.8 meters per second squared, that's acceleration due to gravity, the ball will start out to be going in that straight line, but the second that it falls off the building, it will go under the effects of gravity, in which that it will be going faster and faster in the negative y direction. So at first, your velocity of the golf ball in the y direction is 0. But towards the end, it could be negative 20 meters per second in the y. And also in this situation, we are not taking into account air resistance, so the velocity that the man hits it in the x direction will be constant. So we have our vector here. So our starting velocity, say it's 15 meters per second. At the end, even when we seem to be traveling downward at a very high speed, such as negative 20 meters per second in the y direction, still in the x direction, we will have a velocity of 15 meters per second. And also, as I said, we're not taking into account air resistance, so we won't have acceleration in the x direction unless the object is being acted on by an outside force, such as a rocket or another accelerator, like an engine. So if we go back to our table, you can fill in your velocity in the x direction by finding the sine, cosine, or tangent off of the angle and the original full velocity as the vector. So that will be a constant. That'll go right here and right here. However, when you're finding the velocity in the y direction, that will only be the starting velocity, as there is an acceleration for y. So we know the acceleration for y is negative 9.8 meters per second squared. Well, for a, it's 0. So we're going to do the same exact thing for the x direction in this right triangle. However, with this, we're going to calculate how much time this velocity has been affected by acceleration. So this will be a certain value due to that time, however long the projectile has been sped up by gravity. And for your distance and your finishing distance, that will just be from the origin and wherever on the x and y plane that would land.